In this video we're going to start to look at digital modulation, and we're going to start off with some basics first. When we transmit signals over channels like we looked at in the first video, there are a number of issues that arise, impairments if you like. The first one of these is loss of signal power. And this can be due to resistance if we're using wires, path loss if we're using free space wireless transmission, rain fades, multipath fading, and if we're using optic fibres, then we can also get loss of signal power due to absorption and or scattering. So that's the first thing that we need to worry about is loss of signal power. There's a couple of other things though, in fact many things, but these are some of the more simple ones. Distortion, which is a change in shape of the signal due to different frequency components propagating at different speeds. And noise, there's two main types of noise, natural noise and man-made noise. Natural forms of noise, the most common one of these is thermal noise, which we'll look at shortly, weather noise, galactic noises, and then man-made noises are things like co-channel interference, adjacent channel interference, impulse noises, and various other forms as well. Let's have a look at the first one of these, which is loss of signal power. So, to overcome a loss in signal power, we can amplify the signal with an amplifier. And this diagram here shows the power on a cable as it's transmitted across the entire United States of America. So you can see it starts in San Francisco and goes all the way to New York. And we can see that we transmit initially 1 watt of power between San Francisco, and then as it gets to Sacramento, which is 92 miles, we end up with only about 1/5 of that power. And then you can see it gets boosted up again at Sacramento. So there's an amplifier there, a repeater gain, and then and that repeater gain is 8.3, so it goes up, and then we get a loss again. You can see quite a big loss, and then we boost it up again, this time not quite as high, and so on and so on. So we can see that the signal power remains within a certain range as it goes across the United States. Now we have to boost it up because the receiver has what's called a sensitivity value, where if the signal falls below that sensitivity value, it won't be able to receive the message signal. We'll talk about that in a minute. So we use amplifiers along the way to boost the signal power up, but there's a problem with this, and that is that if there's any noise that gets introduced into the signal, that also gets amplified along the way as well. So in other words, the more times we amplify, we end up with more and more noise. But another problem is that amplifiers are also imperfect. So even if there was no noise introduced on the cable, the amplifiers themselves would introduce noise. So that every time you amplify the signal, you actually degrade the quality slightly. And there is a thing called the noise figure associated with each amplifier. And it's possible to make amplifiers very good, but they still introduce noise. And if we're sending a signal over many thousands of miles, like we've got in this diagram here, we will end up with a pretty ordinary quality signal at the other end. Thermal noise is one of the biggest forms of noise in any telecommunications system, and it comes from the random motion of electrons in conductors. So it's always there. And the power in watts of thermal noise is given by this equation here, 4kTBr, where K is the Boltzmann's constant. Temperature is in degrees Kelvin, which is degrees C plus 273.15. B is bandwidth in hertz, and R is resistance in ohms. So there's always going to be some thermal noise, and in addition, all receivers have a sensitivity value, as I mentioned, which is the minimum power they can receive and still demodulate the signal. Often, if it's a well-designed receiver, that sensitivity is limited by the thermal noise, but it may be constrained by other factors as well. So these things provide a fundamental limit to how far you can transmit a message signal at a given level of quality using analog modulation, because of attenuation in transmission, receiver sensitivity, and imperfect amplification. So you might say, well, let's not have any amplifiers, let's just transmit a huge amount of power at the transmitter, and we'll just wear whatever loss there is in the signal transmission, and we'll receive it at the other end. Well, that may or may not happen because of the sensitivity in the receiver. So that unfortunately means that we do have to use amplifiers, and that introduces additional degradation in the quality. So whenever we use analog transmission, we have these fundamental limitations that are impossible to overcome. But there is a solution, and that is that we can use digital modulation. What's digital modulation? Well, digital modulation is where the message signal is represented in a digital form. But don't get confused that the modulated signal sent over the channel is still an analog signal. So some people get confused and they think digital modulation must be a digital signal that gets sent over the channel. No, it's an analog signal, but the information that's represented on that signal is in a digital form. So there are two steps to the digitization of message signals. The first one we've already seen in the previous video on pulse analog modulation, and that is sampling. Makes the signal discrete in time. Remember, we had the Nyquist sampling criterion, fs greater than or equal to 2b. So sampling makes the signal discrete in time. The second step to create a digital form of the message signal is quantization. Nothing to do with Qantas. It takes the amplitude of the samples and rounds them up or down to the nearest quantization step or level. Let's have a look how that looks here on a graph. The red line here is our original message signal, and the grey line here is our quantized signal, and you can see it consists of lots of little steps. Now, when we quantize a signal, what we're actually doing is in effect introducing a form of error called the quantization error. If we subtract the quantized signal from the original signal, we get this value down the bottom here in orange, which is on an expanded scale, and that's the difference between the original signal and the quantized signal. Now obviously if we use lots and lots of steps, the step size becomes small and the quantization error becomes very small as well. The number of quantization levels is normally an integer power of 2. For example, 2 to the power of 8 or 256 is commonly used in digital telephone systems. In this case, we represent each amplitude level with 8 bits, a bit being a 0 or a 1. So level 0 would be 8 zeros, level 1 7 zeros and a 1, and so on and so on. Level 255, all 1s. So we count the steps upwards in binary. Now, interestingly, CDs, compact discs, use 16 bits for amplitude levels, and if we record a CD carefully, then the quantization error in audio CDs is below the threshold of human hearing. In other words, 16 bits is more than what our ear, the human ear, can hear, and therefore the quantization error is effectively negligible. But for 8 bits, our ear can hear that, but it's certainly good enough to listen to someone's voice on the other end of a telephone connection. So the message signal, once we've quantized it, once we've digitized it, is now just a stream of bits, 1s and 0s, instead of an analog signal. And we can send these bits down the line. And here's the trick. Here's how we overcome that issue that we had with analog transmission. Now what we do is we use what's called a regenerative repeater instead of an amplifier. A regenerative repeater only needs to decide if a 0 or 1 was sent from the received signal, and then it throws that received signal away and it generates a brand new signal to send down the line. So we don't end up introducing noise or distortion into the signal. As long as we receive the 1s and 0s correctly, then what we're actually doing is sending down a brand new digital signal to the next repeater or to the receiver. So therefore we don't have these issues that we had with analog transmission, degradation in quality. So just to summarize, what we've done in digital modulation is we digitize the message signal using a 2-step process. The 2 steps are, first of all, we sample the signal in time. Remember the Nyquist sampling criterion. The sampling frequency f of s has to be greater than or equal to twice the bandwidth of the signal. Otherwise we lose information. So first of all, we make it discrete in time with sampling. Then we quantize each sample to the nearest quantization level. So we have to choose how many levels we're going to use. Normally that's an integer power of 2. And what that step does is introduces quantization noise, but that is under our control. And by choosing an appropriate number of bits, we can make the quantization noise effectively negligible. So now that we've got the signal in a digital form, a stream of 1s and 0s, we can encode a carrier signal with the digital message and transmit that over the channel. But bear in mind that the signal that goes over the channel is still an analog signal. It's just that the information contained in that is in a digital form. And the beauty of this is that we can regenerate the signal along the way so that the only significant noise is the quantization noise and not any other form of noise. In the next video, we're going to be looking at just how do we encode a carrier signal in a digital form, and there's many different ways of doing that, so we'll look at some of those and what are the advantages and disadvantages of different forms of digital modulation.